Welcome to today's RSECTION training. My name is Sonja von Bloh. I hold the training together with my colleague Juliane Stopper. Juliane, perhaps you would like to introduce yourself.
Hello, yes, my name is Juliane Stopper. I'm working in the Dlubal company in customer support, and I'm also supporting the product engineering for geotechnical analysis add-on and reinforced concrete design. And today I will support Sonja with answering your question that you can ask, like she will explain to you. That's it from my side, Sonja.
First, I would like to show you how to use the training interface. It's possible via this button to show or to hide the panel. The settings allow you to adjust your audio settings. There's also a chat function. You can use the window at the bottom to send us questions or comments. We try to answer these questions within the training. If there are too many questions that cannot be answered today, you will definitely receive an email afterwards. You don't have to give hand signals. You can just use the chat function. The training is recorded. This will be sent to you after the training. You also get all the models used. I would now like to give you a brief overview of the training series. In today's training, you will receive an introduction to the strengths of materials. This training builds on the first training, which explained how the internal forces are calculated. In today's training, you will learn how the cross-section values and stresses are calculated. In the upcoming training courses, you will then receive an introduction to finite element analysis and then an introduction to our design modules. This brings me to today's training program. I will first give you an introduction to the RSECTION program. Using several examples, I would like to show you the modeling options and design methods in the program. In the first example, a thin-walled eye section is modeled with graphic functions. I will model this slowly so that you can enter this cross-section as well. In another example, I show how to insert cross-sections from the database and how you can add other parts to these cross-sections. Then I show the modeling of a massive cross-section based on a DXF template. Finally, I model a hybrid cross-section. First, I start a survey. To find out whether strengths of materials has already been covered in your studies. I ask you to answer this now. Most of you has answered now, and you can see the result here. Most of you have already taken classes in strengths of materials. Okay. Then I would ask you to answer the following survey. If you are working with 2 screens or monitors, I will adjust my pace accordingly. Okay, most of you are not working with 2 screens, so I will make it a little bit slower. Okay, then I will show you the RSECTION interface. RSECTION is an independently executable program for generating any thin-walled or massive cross-sections. If you want to design special cross-sections in RFEM or RStab that are not contained in the cross-section library, you can create them with RSECTION. You can then import these user-defined cross-sections into RFEM or RStab. In RSECTION, it's possible to calculate cross-section values and stresses. The RSECTION user interface is the same like in RFEM 6 or RStab 9. The cross-section graphics and dialogues are displayed in the working window here. Most tasks can be performed with the mouse. In the table here in the bottom, the keyboard is primarily used for numeric input, and you will find out also the output of the calculated results. Here on the left, you see 3 navigators. It's the navigator data, the navigator display, and the navigator for results. The data navigator manages the input data. A double click here, if I open this tree here on an object, maybe here the points opens the corresponding dialog in which the selected object can be changed. However, it's also possible to create new objects. If you right click on an object, you will find here the corresponding functions. Then I will go to the navigator display. The display navigator controls the graphical display in the working window. If the checkbox in front of an entry is unchecked, this object is hidden in the graphic. If I here uncheck the points, then you will see here in the graphic the points are not displayed anymore. Then I would show you the navigator results. Here the navigator results controls which results are displayed. You can here switch between ordinates, stresses, and so on. Then I would like to go into the mouse functions. To move the section, you can hold down the mouse wheel and move the section accordingly. You can turn the mouse wheel to zoom in or to zoom out. Then you can right click to open the context menu. You can also select objects with the mouse. If you open a window from left to right, everything that is completely within the selection area will be selected. Here, these objects were completely in the selection area, so they are now selected. What you can see here with this yellow color. If you drag a window from right to left, everything that is intersected by the selection area will be selected. You can see here now that also here this part is selected because it was intersected by this window. You can also select individual objects to do this. Left click on the objects to be selected. Here I want to select this point, so I have to left click on it. And if I want to add another object to the selection, I have to hold down the Control key, and then you can see here the mouse pointer shows a plus, and then I can select the other object. it's also possible to remove objects from the selection. Then I have to hold down the Shift key. You can see here my mouse pointer now shows a minus symbol, and then I have to here select the object that I want to remove from the selection. For the first part of the training, I'm now starting a survey again. I will do this. Please answer the following question about the suitability of our section. Multiple selection is also possible. I will now share the results. Sorry, I have closed it, but all answers were correct. Our section is suited for the creation of any thin-walled or massive cross-section, and also for the calculation of cross-section properties and stresses. This brings me to the first example. To create a custom cross-section, I have to create a new file, and I will do this via this button, New Model. And then I first have to enter the cross-section name, and I name it Example 1. Furthermore, the analysis method must be defined. I have here two possibilities. I have the finite element analysis and the thin-walled analysis. I choose the thin-walled analysis in this case. The effective cross-section can be calculated for both analysis methods. After activating here the option effective section, standard must be selected, and here several standards are implemented. It's here Eurocode 3 part 1.1, Eurocode 3 part 1.3 for cold form sections, and Eurocode 9 for aluminum sections. I choose here this standard for Eurocode 3 part 1.1, and according to the standard and the rules described in the standard, the subpanels are to be generated and the effective cross-section is to be calculated. The selection of the analysis method or the standard is irrelevant when using the RSECTION cross-section in RFEM or RStab. You can select the design method in RFEM RStab regardless of what is set in RSECTION. Furthermore, the subpanels are generated in the design modules based on the standard selected in the design add-on. In the steel add-on, the manufacturing type, what you can see here, determines which part of the standard is used for the design. For a cold-formed cross-section, that's this here, the standard Eurocode 3 part 1.3 is used, and for hot rolled or welded sections, the standard Eurocode 3 part 1.1 is used. I don't define a manufacturing type here in this case. Then I click on OK, and a new file will be created. And first I define the material. Here already two materials are defined. If I double click on it, I will open here the edit material dialog. If no materials are defined, then it's also possible to right click on this material and then create here a new material. Okay, I open this dialog again, and I can create here on the list via the button create new material, a new material, or it's also possible to copy selected materials. I can enter here, if I click on this button user defined name, a name directly, and RSECTION, if I type in this name, lists all materials that match that name. But it's also possible to open the material library via this button. And I will do this in this case. And here in the material library, filters are available here on the left to quickly find the material. Here, maybe I can choose steel, then here on the right, all steel materials are listed. Here also a search is available, in which I can search for a material, and I search here for S355. And then I choose here this standard, and here this material, and then I click on OK. If the material is not in the material library, I can create this material. If I activate here this checkbox user-defined material, and then it's possible here in the following tabs to define the properties that I want to use. I don't do this today, so I deactivate this option again, and then I click on OK. I then create the elements. The definition of elements is required if the analysis method, analysis of thin wall structures, is selected, or if the effective cross-section is to be calculated. An element must always lie in an area, and this area is called an RSECTION part. Elements can be created graphically or via a dialog. The graphical input is called up via the symbols that you can find here. And the input via a dialog is called up via this navigator data. Here you can create a new element. When creating an element via the graphical input, the part is also created. When creating an element via the dialog box, the parts and the points of the element must be created beforehand. That's why I can choose this dialog now, because I haven't created the points before. So I choose this function for the creation of elements. Here I choose single. I enter the bottom flange here first, and for this I use the input mode length and direction, and here I define an angle of 0 degree, and I define a length of 150 millimeter and a thickness of 10.7 millimeter. Then I can insert this element in the working area graphically, or it's also possible to define here the point coordinates. I put this here on the coordinates 0, 0. And for this, I left click here in the working area. Then I create the web. And for this, I use the input mode length and direction again. And here I define an angle of 90 degrees. And you can see here what's happening. And now I reverse the orientation. And I define here a length of 289.3 millimeter and a thickness of 7.1 millimeter. And then I left click here on this node. Elements must be connected for the calculation of the effective cross-section. The connection is to be made via the start and end points of the elements. If two elements share the same points, they are connected. I have now here this element, and they share here this point, so they are connected. Then I create the left flange. For this, I use here the length and direction input mode again. And here I define an angle of 0 degree and a length of 75 millimeters and a thickness of 10.7 millimeters. And then I left click here on this point. Then I reverse the orientation again, and I left click on this point again. Okay. The cross-section should be a rolled T cross-section to which a lower flange is welded. The round radius is 15 millimeter. I can define lines to create them or use a function that's called create round corners. I find this function here, create round corners, and I click on it, and then I define a round radius of 15 millimeters, and then I have to left click here on the corresponding lines. And if I right click on the mouse, I leave the dialog, or I close the dialog. Then I have to define the welds. So for this, I use the function create angled corner. And here you have two corner types, both edges and edge and angle. And I choose here the edge and angle corner type. The lower flange is welded with a 6 millimeter double fillet weld. And I choose, I can type in here the length, or it's also possible to calculate it in this dialog. So I define here 6 multiplied by the square root of 2. And then I have to define the angle, and the angle is 45 degrees. Then I have to click on the corresponding lines. And now my welds are created. What you can see here are the sub-panels, and these sub-panels are automatically generated based on the standard selected in the base data dialog, and these cannot be changed. If no elements are defined, the cross-section classification in RSECTION and the design and in the design modules of RFEM or RStab is not possible. And it's also not possible to do a calculation of the effective cross-section if no elements and no subpanels are defined. In the design add-ons of RFEM or RStab, like steel design, the cross-section is then designed according to the cross-section class 3. I would also like to use this example to show you how to calculate stresses and the effective cross-section. And in order to calculate stresses or the effective cross-section, a load case must first be created. Load combinations can also be created, and I create a load case now. And I do this via the navigator data. For this, I right-click on the load case, and then I choose a new load case. Then I can define a load case name if I want to, and I name it N, and then I create a second load case via this button here, create new load case, and I give the load case the name M. Then I define a load combination via this button. And here I assign these two load cases for the load combination. It's also possible to define here a factor if I want to. And here it's also possible to rename that load combination, and I name it N plus M. And then I click on OK. The internal forces can then be defined manually or imported from RStab or RFEM. To import the internal forces, you have to click here in the table internal forces, and then you have here the possibility, if you click on this, to import internal forces from RFEM or RStab. I don't want to show this today. I want to define the internal forces manually. So I go to the navigator data again, to internal forces, and then I double click on internal forces, and then I define a load case N, in load case number 1, an axial force of minus 10 kilonewton. Compressive forces are negative, tensile forces are positive. The axial force acts in the center of gravity of the cross-section. Here I click on Apply and Next, and then I choose the load case to load case number 2. And here I want to define not an axial force, so I define it here to 0. And I want to define here a bending moment about the y-axis, and here I define 100 kilonewton meter. And then I click on OK. In the navigator data, you can now see here in load case 1 an axial force of minus 10 kilonewton is defined, and in load case number 2, bending moment about 100 kilonewton meter is defined. The blue dots that you can see here on the graphic are the stress points. Stresses are calculated and displayed at the stress points. the stress points are generated automatically. Stress points can also be defined manually, and I want to do that here. So I go to the navigator data again, and then I go to stress points. I right click on stress points and choose here new stress point. Then I can define the point number if I want to. I define here 100, and then I have to define the coordinates, and Y I define 75 millimeter and in Z minus 100 millimeter. And then I click on OK, and the stress points will be generated. You can see it if you go with your mouse upon the stress point. It's also possible to show the numbering. You can right click here and choose show numbering. Then you can see here, okay, this is the stress point 100. I deactivate this numbering again. It's also possible to show the numbering via the navigator display. Here you have this checkbox numbering, and here you can select or deselect the display of points, lines, and so on if you want to. Which stresses are to be calculated and output in tabular and graphical form can be set in the stress configuration. I will show you this now. For this, I go to the navigator data again, and then I go here to stresses, stress configuration, and I double click on the stress configuration, and the corresponding checkboxes are to be activated or deactivated here. If I click on this entry, then you get an information how the stress is calculated. Then I click here on OK. I start the calculation now. And in the result navigator here, you can switch between the results of the gross cross-section. That's here the thin-walled analysis. I can show you here the stresses maybe, and this is for this load case number 2, and you can switch here also. You can see here the stresses from load case number 1 or from the load combination. I choose here load case 1. There was an axial force defined, and it's also possible to change the type of display. Here I choose off, and it's also here possible to show the different section properties. You can show here the statical moments, or the ordinates, or unit stresses, or the stresses. Then it's also possible to show here the effective thin-walled, the effective cross-section, and you can see here in the graphic in the working window that this cross-section falls into class 4. Here this cross-section is reduced. According to the standard, the reduction in strength due to local buckling can be taken into account through effective width, and this is implemented in RSECTION. It's also possible to display or to control the section properties in numerical form. For this, you have here also the possibility to show you the section properties of the gross cross-section. For this, you have to choose here thin wall analysis, and then you have to have the possibility to show the section properties here via this drop down. And here you can see the sectional area that's calculated for the cross-section, and the area moment of inertia about y-axis and z-axis and so on. And it's also possible to show here the statical moments and warping in numerical form, and also here the stresses. Furthermore, it's possible to show in numerical form the effective cross-section. Here you have the effective section properties, and also you have the section classification, and you see here the section falls into class 4. And if you click on this subpanel, then you see, okay, this subpanel falls into class 4, and these subpanels fall into class 1. And you can also see here the effective widths that are calculated. I'm now starting a survey again regarding the requirements for cross-sectional classification. Multiple selection is here also possible. Okay, I now will show you the results. And for a classification, internal forces must be defined, elements must be defined, and it's necessary to activate the effective section add-on. Okay, I would now like to use another example to show you how you can access cross-sections from the library and modify them. For this, I create a new file. I click here on new file and I name it example 2. I choose the analysis method thin wall analysis, and I choose here also the option effective section and the standard EC3 part 1.1. And I click on OK. I define the material first. For this, I modify this material. This is the material that I wanted to use, but I show you the material library again. I can click on this button, import from material library, and then I search for the material that I want to use. It's an S235. I choose this material, click on OK, and OK. And then I insert a cross-section from the cross-section library. To do this, I right-click here in Navigator on the tree section and choose New Section. The window is structured like the material window. a cross-section can be created here via this button, Create New Cross-Section. It's also possible to copy a selected section, and also possible to type in here the name of the cross-section, maybe here EPE 200. And then all cross-section that match with the name are listed here in the list. It's also possible to open the cross-section library via this button here, Import Section from Library. And then I have to select the section from the library. And here I choose the L section. Here again, the cross-section library is in the same way structured like the material library. You have here filters on the left, where you can filter from manufacturer, for example. And it's also possible to search for a cross-section. And here I type in L 200, 150, 200, 0 was missing, 150, and 12. And here I choose this standard, and then this section, and I click on OK. The angle should be mirrored around the y-axis. So I activate the checkbox about y-axis, and the section should be rotated by 90 degree. So I type in here 90 degree. Furthermore, I select here the offset point in the graphic, and this is this point. And at this point, the cross-section is placed at the insertion point, and the insertion point I can define it manually here in these boxes, or it's also possible to pick this in the working window. I will do this. I pick here the 0, 0, and then I click on OK. When inserting this thin-walled cross-section, here 2 elements were defined, and also the part. The cross-section can be subsequently edited. If I double-click on this cross-section, I open the Edit Section window, and here I can change the section location or the mirroring, and I can also change here the cross-section. I can import another cross-section from the library. It's also possible to move or mirror this cross-section via these function, move, copy, or mirror. And however, in order to modify individual objects, such as points or lines, the cross-section must be splitted. The cross-section is to be supplemented by further cross-section parts. I therefore split the cross-section into its individual parts for further processing. And for doing this, I first deactivate here this function auto-split element. And then I right-click on the section and choose here the function convert into normal geometry. Now this cross-section is splitted into its objects, and the fillet isn't needed, so I delete this point, And with deleting this point, the fillet is also deleted. And now you can see that the elements are colored in red. And this red color says, okay, there's something wrong. And here the part is missing. You can see the part was also deleted and elements must lie in a part. So now these elements are shown in red. Okay. I also add then more elements, and I do this via the graphical input. I choose here single, and I use the input mode length and direction again. Here I define an angle of 0 degree, and I define here a length of 200 millimeter and a thickness of 12 millimeter. And I want to place this here, and for this I have to reverse the orientation, and then I left click here in this working window, and then I add another element here with an angle in the work plane of 90 degree. I have to reverse the orientation again, so I click on this button. Then I define a length of 400 millimeter and a thickness of 10 millimeter, and then I left click here on this point. Then I right click so that this window is closed, and I don't need these lines here. So I delete them. I press here the delete button. I do this for this line also. Press on delete. Welding seams should also be taken into account in the cross-section properties, and I create the weld seams using the angle corner function that I've shown you before in another example. So I click here on the button create angled corner. I use the corner type edge and angle again, and here a 6 millimeter double fillet weld is to be defined, so that I define here 6 multiplied by square root of 2, and I define here an angle of 45 degree, and then I click on the corresponding lines. Furthermore, I still have to create the part by selecting the relevant lines, and for this I use the function that you can find here, select boundary. Here I have to define the material for the part, then I click on OK, and then I click on the line, and the part is created. And what you can see here, now the red color for the elements are gone, because here now the part, what's necessary for the elements is created. I would now like to calculate the effective cross-section and the stresses, so that I create a load case and internal forces. To do this, I right click here on new load case, and I type in the name N. I add another load case with load case name M, and also a load combination. Here I change the name to N plus M. Then I click on OK. Then I have to define the internal forces For this, I double click on the internal forces, and I define here an axial force of minus 50 kilonewton for load case N. Apply and next. Then I change to load case 2. Define here an axial force of 0 kilonewton and a bending moment of 20 kilonewton meter. And click on OK. I start the calculation now. And I can see here the effective cross-section. I change here the type of display to off, and I want to see the stresses. And I see now here the reduction due to the class 4 cross-section. I can control this here in numerical form, section classification, okay, it's class 4. And I can see here also the calculated reduction. I want to create a printout for the documentation, and to do this, I go here to Navigator Data again. Then I right-click on the printout report and choose New Printout Report. And then I can choose the report items. I don't want to have the stresses by material, by member, location, stress points, or stresses by stress points here. And I don't want to see the stresses by loading and material here. Then I click on Save and Show, and the printout will be generated. You can see it here. And it's also possible to add a graphic to this printout. For this, I go to this button here, print graphics to the printout, and maybe I can change here a little bit the representation. Maybe I can add here all values, and I want to tilt the result diagram into the work plane. And then I choose this print graphics to the printout report again. And here it's also possible to influence the size of the picture here. I can choose here window filling, then it's much more bigger. And then I click on Save and Show. And then this graphic will be added to the printout. I'm starting a survey again. Please answer if an analysis of thin-walled structures is suitable for the calculation of a rolled parametric steel section. Most of you have now answered, so I close the survey again and I share the results. And a correct answer is here that the analysis of thin-walled structures is suitable for the calculation of rolled and parametric steel sections. In my first example, I show my screen again, and I close here the printout report, and I go to my first example again. I forgot to show you how to display the stresses on a certain stress points. For this, you remember maybe we have created stress point number 100. And if you want to see the stresses on stress point number 100 in the table, then you have to choose the table stresses, and then you click onto the stress point. And now you see here the stresses here on this stress point. I forgot to show you this. Okay. In the next example, I would like to show you that you can also create cross-sections by importing a DXF file. A DXF file can be imported via menu File, Import DXF. Then you have to choose the corresponding DXF file, click on Open. And here in this window, I can specify the insert point and the rotation here. And it's also possible to switch the coordinates. And in this section, create a section model, you have 3 options for creating the cross-section. And here the option to create all elements automatically is useful if the outlines of the cross-sections are available in the DXF file. Our section attempts to create center lines for parallel lines and then set the elements between the intersections. Only elements that do not exceed the maximum thickness defined here in the maximum thickness field are created. And then this import function use DXF templates lines as center lines is useful if the cross-section geometry is available as a centerline model. You can then import this cross-section, and then the elements are created on the center lines with a thickness that you can define here. Then the function create DXF template is useful for massive cross-sections where no elements need to be created. In addition, this function can also be used for complex cross-sections where I only want to create elements for the decisive cross-section parts. And with this import functions, the lines in the DXF file are imported as lines. And I use this function here now. So I click on OK. And now the cross-section is imported. And first I define the material for this cross-section. So I go to the navigator data again, click on materials, double click on this material, and I want to choose an aluminum material from the material library. So I open the material library again, and then I can choose here aluminum, and here I search for EN 6060. And then I choose this material. And I click on OK. Then I open the base data. And here I have to choose the analysis method, and a finite element analysis is to be carried out for this cross-section. So I choose here the finite element analysis. Finite element analysis should be performed on massive cross-sections such as timber cross-sections or concrete cross-sections, in contrast to thin-walled cross-sections, where the stresses can be regarded as constant across the cross-section thickness. The stress distribution in massive cross-sections is variable. And this can only be determined with a finite element analysis. So I choose this analysis method. Then I click here on OK. In a finite element analysis, only a part need to be defined. It's not necessary to define elements. So I define now this part. And for this, I use the function select boundary. Then I choose here the material ENRW6060. Click on OK. Then I choose the line, and the part will be created. After creating the part, I still need to create the openings. I use also here the function select boundary for openings, and then I choose here the corresponding lines. And I want to show you that you can also create openings with the function rotating. So I now select the opening that I want to rotate and copy, and then I select the function rotate selected objects. Then, because I want to create this opening, I activate the checkbox create copy. I want to have 3 copies, and then I have to define the point of rotation. I can pick it in the work window, and then I click on OK. Oops. Sorry, I forgot to define the rotation angle. This should be 90 degrees. And then I click on OK. And now the openings are created. I want to calculate the stresses here as well. So I create a load case, new load case, and I name it N plus MT. Then I click here on OK. Then I have to define the internal forces. And here I define a compressive force of minus 10 kilonewton. And here I define a torsional moment about 0.3 kilonewton meter. And I click here on OK. And then I start the calculation. And here in the navigator results, I have only the results of the finite element analysis. And here I choose the stresses, the equivalent stresses here. And you can see now the graphical results on the working window. I'm starting a survey again. So I choose it first. Please answer whether the finite element method is suitable for the calculation of massive cross-sections, such as concrete or timber cross-sections. Okay, I now close the survey and I share the results. 100% have answered right, and this is also the correct answer to this question. Okay, as a last example, I show the modeling of a composite cross-section. In RSECTION, it's also possible to model cross-sections that consists of different materials. Ideal cross-section values are determined for such a cross-section. For this, I create a new file and I name it example 4. Here I choose the analysis method finite element analysis and I click on OK. Then I have to define the materials. For this, I modify the first material, and here I open the material library again, and I want to use a steel material S235. So I choose this material. And for the second material, if you don't have one, I will delete it. If you don't have one, you can create it via this button, Create New Material. And then you can go to the material library, and then you can choose here concrete for material type. And then I choose here C4050. I click on OK and OK. 1000 millimeter wide and 200 millimeter high concrete cross section lying on a AHB steel cross section is to be modeled. So I model the concrete cross section. For this, I use here this function single element. I use the input mode length and direction, and I define here a length of 1000 millimeters and a thickness of 200 millimeters, and I choose here the material 2, the concrete material, and then I add this here in the working window with right click. I close the window, and then I select AHB 400 from the cross-section library. To do this, I right-click here on Section, New Section. I open the section library, choose here I-beams, H-beams, and then I type in AHB. Here I want to use this cross-section, and I choose here the material, the steel material number 1 S235. Click on OK. Then I pick here this point, and I pick here this location, and then I click on OK. Now I have here 2 lines. This is not so good for the calculation. That's why I right click on the section and I convert it into normal geometry. And I have also here the 2 lines, but it's possible here with this function, connect lines and elements. I go here by these lines, right click, and then you will see we have only 1 line. Then I create a load case for the bending moment. Here, new load case. I name it M. Click on OK. And I define an internal force of 100 kilonewton meter. And click on OK, and then I can calculate this cross-section, and in the section properties you can see that the ideal section properties will be calculated. The reference material is always the first material that I've defined, here in this case the S235, and you can also see here the geometric sectional area. I would also like to show you how to import the cross-section into RFEM. To do this, I save this cross-section, and now I open RFEM. And to import the cross-section, I go here to the navigator data again and right-click on the section, new section. Then I open the section library, and here we have a button for importing cross-sections made with RSECTION. So I click on this button. Then I choose here my cross-section that I've created and click on Open. Now this cross-section will be imported, and you see that this checkbox hybrid is activated. And here in the tab hybrid, you see the material assignment. You can see here now for parts number 2, the material S235 is assigned. Then I click here on OK. It's also possible to change it here if you want to. And it's also possible here to choose a different material. You can create it also here in this dialog. Maybe here an S355. And here, maybe it's better here to use this material. And here, different material. Sorry. I have made a mistake. I choose here the concrete material. Okay. Okay. So you see, you can change it by your needs, and it's now possible to use this cross-section in a member. For this, I create a new member. Here I can choose the section. And now I've created that member with this cross section. With this example, I have come to the end of the training. It was taught how you can create general cross sections with graphic functions, how you can add cross-section parts to database sections and create sections based on DXF import. Finally, I would like to show you where you can find more information. For this, I open our webpage here at Dlubal.com, and here on tab Education, you can choose maybe here RFEM 6 for students. Then you can open here the knowledge base, or it's also possible here via support and learning to open frequently asked questions. I hope that the training for using our section has helped you, and thank you for your attention.